Okay, and then next layer is MAC layer, and MAC layer supports all the scheduling part for downlink and uplink, and help retransmission, error retransmission. So those kind of things are done by MAC. All right, and REST procedures and binding advanced aspect are all there in LTE. That also support in 5G. So what is new now is since we are going to have multiple numerologies at MAC. So let's assume you are doing carrier aggregation and assume it is dual connectivity. So you may be having one carrier with 15 kilohertz and the other carrier is 50 kilohertz. So those can be possible, and MAC is the one who is going to handle that multiple numerology aspect because the task is for scheduling. So one of the key MAC tasks is the beam management. We will talk in detail about beam management in the core processing part later. Right? And the last part is physical layer. There are some changes there. Okay? Physical layer is the lowest layer of the protocol stack, and it deals with the transmission reception of the physical signals over the interface. And some new channels are added in this red color. The red color are the new ones. And other channels are pretty much the same as what we have in LTE. Okay, like random in the case of uplink, we have REST channel, PSCH for uplink data, UCCH for the uplink control. Okay, same. Only things that is different, we are now have PTRS, phase tracking reference signal. So similar to the downlink, the new fix is PTRS and TRS. So basically on the uplink, there is more about that, and on the downlink, we call it sync signal. Right, so we will dig more into sync signal in the next part. Now we're talking about what are sync signal, synchronization signals. So signals are nothing but we have like two signals, okay, PSS and SSS, which is primary sync signal and secondary sync signal. Okay, so it's like a two-step synchronization so that the UE can acquire that channel. All right. So let's take a look what happened when we turn on our mobile phone. For example, our mobile phone are in idle condition. So when we turn on our phone, that's when the sync signal activates, right? First thing, right after the sync is UE need to know which cell they want to register. Okay, the GNOP, and then the GNOP will continuously send the sync signals every 20 milliseconds, and then the UE will select which cell that has the strongest bit for sure, and then the GNOP will send bit, seeds, and all that information, and why we need to synchronize because we need to know their physical cell ID, their PCI, because PCI is important for data transmission. So when we acquire the PCI, only then the sync signal will send the data from the nearest base station, right? And the difference that you may find compared to LTE is sync signal carrier spacing varies with that channel. And if you are in sub-6, you have 15 and 30 kilohertz sub-carrier spacing allowed, and you are in millimeter wave, you can have up to 240 sub-carrier spacing. All right, let's take a little step back. Now we need to go on let PSS and SSS signal where we can find them. Okay, so that's the thing we need to resolve. Once it powers up, once the phone is powered up, first it needs to resolve where to look for this PSS and SSS. So in the case of LTE, we always know that the PSS and SSS are sync signals and are always transmit in the center frequency. But in the case of 5G, again, the way 5G is defined is very flexible. So sync signals are no longer present at the center. So it can be anywhere in the channel bandwidth, right? So that's the flexibility provided in something so that can bring us the need to have a new raster, which is called sync raster. Okay, maybe see in the table, in 3G, in 3 gigahertz, which is equivalent to 3000 megahertz. Within this frequency range, the UE is going to set that channel at the step of 1.2 megahertz size. Okay, but for this range, your step cell is going to be 1.44, and in the millimeter wave range, the step cell is slightly large, which is 17.82 megahertz. Okay, so now synchronous is used in this case to find out where the PSS and SSS is located within the channel bandwidth. Okay, so here's 3GPP defines what are the subcarrier spacing allowed for the SSD in signal block. Okay, so for example, if you are in the N1, okay, you don't need to worry about what subcarrier spacing going to be. So it can blindly use 15 kilohertz subcarrier spacing to find the PSS and SSS. However, there are some channels like we have seen here, N5, N41, and N66, where you may have more than one subcarrier spacing for the given channel. And in this case, you need to try to acquire with a different subcarrier spacing. And it may succeed with one or another. And in this flexible given, you can use both 15 and 30 kilohertz. All right. Okay, so now how is PSS and SSS is going to be transmitted in the case of 5G? And what we have here is we have this one is sync signal block, which comprises of PSS and SSS. Okay, on a SSS, PSS on the symbol 0 and SSS on the symbol 2. Okay, and you also can transmit PBCH here on symbol 1, PBCH on symbol 2, and PBCH on symbol 3. Right, so we combine the entire thing, so we call this as sync signal block. All right, so your PSS is your, as I said, primary sync signal, and SSS is your secondary sync signal. So these signals are needed to get the slot frame and the symbol type. And the PBCH is the first thing, the first system information that you are going to get, which contain MIT that's going to be decoded in that PBCH. So MIT contains all the information that is required, like frame number, physical cell ID, and all that information. All right. So, all right. So this entire block is a total of 4 symbol lines, and it can occupy so 20 resource blocks in the frequency domain, and the PBCH is around 240 subcarrier spacing. Okay, but your PSS and SSS only takes about 127 subcarriers. All right, they are placed like left over here, as you can see, no transmission here. Okay, while the left is space empty. Okay, because they want to facilitate, like to easily to find out the PSS and SSS. Okay, so it's like to help the UE to quickly determine where is the PSS and SSS, and then we can go and file and get the type. Okay. And then this is the PBCH block. Okay, so this slide just want to show the maximum number of SSD, right, within the SSD set. If the frequency is less than 3 gigahertz, the subcarrier spacing 15 kilohertz, so the maximum number of SSP is going to be 4. So it's unassigned. So this is the figure how the SSP was set. So one SSP was set can consist up to maximum number of SSP. Okay, so one SSP. Alright, and the maximum number of SSP, it depends on the carrier frequency and subcarrier spacing. Okay, so this is the payload. Payload meaning data. Okay, data for PDC. Alright, and then this is the SIP overview, the comparison between 4G and 5G. Okay, so the system information is similar for 5G and LTE, where SI is grouped into mid and several sheets based on the content. And the difference is there is in 5G, there is an option to broadcast only part of the information. While in LTE, the system information is always broadcast, right? Okay, so this is the NSA system information acquisition. So this one shows we can see how is the process when we turn on our mobile phone and how we want to attach within one cell. All right, what we need to do is synchronization and information acquisition. So for NSA system, firstly, they need to attach to LTE first, okay? Meaning that now we are in LTE connected mode, okay? So we know there are NR connection as well, and then we read